Hello and welcome to Graphing and Functions, Input and Output. In this discussion, we'll begin by talking about the rectangular coordinate system and a list of terminology that you should understand. In a rectangular coordinate system, you have two number lines, a horizontal number line called the x-axis and a vertical number line called the y-axis. Here you will see the horizontal number line is labeled x and the vertical number line is labeled y. In this coordinate system, we will graph ordered pairs, and they will consist of an x-coordinate and a y-coordinate. So you will be given an ordered pair written in this form, x, y, with parentheses around it, where the first value is called the x-coordinate and the second value is called the y-coordinate. The first point you need to learn is the point called the origin, and this is located at 0, 0, and that is at the point of intersection of the two number lines. So this point is called the origin and can be labeled with the ordered pair 0, 0. These two number lines divide our coordinate plane, that is our flat surface here, into four areas called quadrants, quad meaning four, and they are labeled as followed. In the upper right hand corner we have quadrant 1, followed by, going counterclockwise, quadrant 2. Quadrant 3 is the lower left hand quadrant, and quadrant 4 is the lower right hand section of the coordinate plane. Now when you are plotting points in these quadrants, the order that the coordinates are given will matter, and that is why these are called ordered pairs. So let's look at a couple of examples. If I were to put a point here, this point would be located at an x-coordinate of 4 and a y-coordinate of 8. So we say that the ordered pair for this point is 4, 8. Now that is different from 8, 4. The ordered pair 8, 4, while still located in the first quadrant, is at a different place because the first coordinate is the x-coordinate and it's 8, and the second coordinate is the y-coordinate and it's 4. So you can see why the order of these values does matter, because the position will be different depending on the coordinates that are given. So in order to plot a point, you can see what I did here. You take the first coordinate located on the x-axis, take the second coordinate located on the y-axis, and then you can find your point. So if I want to plot the point 3, -5, my x-coordinate is 3, so I will go over to 3 on the x-axis. And then actually I'll go down 5 because -5 is here. And so 3, -5 is going to be located here, to the right 3 and down 5 from the origin. So the first coordinate tells you which way to move along the x-axis, left or right. Right if it's positive, left if it's negative. The second, or y-coordinate, tells you which way to move along the y direction, up if it's positive, down if it's negative. So these are going to be always xy. Let's do another one. -2, -5. In this case, x is -2, so starting again at the origin to -2, and then down to -5 would be here. -2, -5. Let's do -3, 7. -3, still left 3. 7 is up 7. So this is the location of the point -3, 7. And you can see that it's 3 to the left and up 7. Sometimes your point's going to actually be on an axis. So let's say we have the ordered pair 0, 2. Well, our x value is 0, which means we move neither left or right. We stay at the origin and then we move up 2, and so our point 0, 2 is actually located on the y-axis. And you can see a similar thing for points that are located on the x-axis, like -7, 0. We would move to the left 7, but since our y-coordinate is 0, we would stay right here on the x-axis at -7, 0. So in order to plot points, generally speaking, you can just start at the origin, look at your first coordinate or your x-coordinate, decide if you should go to the right or the left, depending on if it's positive or negative, or if it's 0, do not move in either direction, and then look at the y-coordinate to decide if you should move up or down. Now we'll use the method of plot pointing to graph an equation. So we'll have to do a little bit of algebra or arithmetic here in order to graph this equation. Notice that we are given that the value of y is equal to x squared, subtract 3 times x, subtract 4. I'm just going to pick some values here, somewhat at random, so we can get an idea of what this shape would look like. If I pick x to be 0, I have 0 squared minus 3 times 0, subtract 4, and that would calculate out to be -4, which means my ordered pair would be x is 0, y is -4. So as we saw a few minutes ago, that point would be located on the y-axis, down 4, because we do not move to the left or right. If the x-coordinate is 0, we just move down 4. I'll actually label this with point A so that we can keep up with our points here on our graph. For the second value, we're going to take 2 squared minus 3 times 2, subtract 4, and so I'm substituting in for the value x, the given value of x here in my table. 2 squared is 4 minus 6, -2, subtract 4 is -6. So if x is 2, y is -6, that will be our point B. 2 down 6. Now the next value I have for x is -1. And in order to do this without missing a sign, I need to put my substituted value inside of parentheses. And then I can do my arithmetic. -1 squared is going to be 1. I'm just going to write it down here at the bottom. I'm going to get a +3 because a negative times a negative is a positive, and then a subtract 4. Left to right, 4 minus 4 would give me 0. So if x is -1, y is going to be 0, and that's our point C. -1, 0 for our point C. Starting to get an idea of what the shape looks like, but still don't have an exact idea of what it looks like. So I'm going to continue here with the next value, -2 minus 3 times -2, subtract 4, and that's going to be -2 squared, by the way. So that's going to be a 4 plus 6 minus 4. That's going to come out to be 6. -2, 6. It's up here. We'll label that point D. And we're starting to get an idea of what the shape might look like on this side, but I'm not sure what's going on out here. Now, I had a value of 1 in my table, but since I'm trying to figure out what's going on over here on this side, I'm just going to change that and try to find out what's happening at 5. So 5 squared minus 3 times 5 minus 4. Again, I'm substituting the value for x into the equation. If it's negative, I need to put the parentheses around it. If it's not negative, I'm okay. I can just write it. 25 minus 15 is 10 minus 4 is 6. So if x is 5, y is 6. So that's x is 5, y is 6. That's going to be my point E. Let's do one last point and to just sort of get the idea here, and I think I'll go ahead and do the value x is 4. So 4 squared, 3 times 4 minus 4 would be 16 minus 12 minus 4. That's actually 0. So if x is 4, y is 0. And so here's my point that I'm going to label F. And so what we see here is that we have a shape that's actually what we would call a parabola. And I'm going to try to kind of sketch it in here. It's not going to be a perfect hand sketch, but it's a U shape that would sort of connect these points together. Like this, something like this. And obviously I could get a much better picture. I'm going to switch over right now to show you what this would look like in a little bit better format. And so this is a little bit better picture of the way the curve would actually look if you were to plot all the points for x and then calculate their y values. It would be a smooth curve like this that's called a parabola. And later on we'll learn how to recognize what the graph would look like, but the important thing at this point is recognizing how to plot the points and how to do the arithmetic in order to find the y coordinate if you know what the x coordinate is. So here we have a slightly different situation where we're given two equations, and we're going to also plot points and graph them on this coordinate plane. We're going to graph them on the same coordinate plane. A few values for x. And again, complete by substituting the value you have and then writing your ordered pair after you've done your arithmetic. And I'll locate the approximate location of these guys just by putting a little mark here. 214 would be up here somewhere. And then 526 up here. And so basically I have a straight line that goes approximately through these points. It looks something like this. Then I will repeat the process for the second equation. Again, pick a few values. Now at this point I'm basically randomly picking some values. However, there are ways later on that we'll figure out which values to select in order to be the most efficient in selecting our points. Substituting in. This time we get 0, 0, 210, and 420. And so drawing in the second line, y equals 5x, by plotting these points, I get, and we can see that we have a graph of two lines here, and they actually intersect at a point, and we'll be talking about that in just a little while, about this point of intersection of this graph and what it means. But this is just a rough sketch. We just want to plot the points, get a general idea of what it looks like, and then we can be a little bit more precise later on when we have to be. And so now we want to talk about a function and this concept of dependability. And there's a picture here drawn of what might be considered a function machine. But let's talk about the definition of a function. A function is a rule that assigns each input value to one and only one output value. So when you have a function, some value will go into the function, some value will come out of the function, and inside the function some operation or rule is being applied. It doesn't necessarily have to be values, but generally speaking, we'll be working with functions that do process numerical information. Now, a function must be dependable. What that means is that each time you put in the same input value, you must be able to depend on the exact same output value being generated each time. Because remember, this rule is going to be consistent. Whatever the rule is will be applied every single time. So if you put in the same value, you would expect the matching output value to come out each time. I'll give you some examples in a minute and make a little bit more sense, I hope. Now, the rule, if you're talking about an algebraic function, is the mathematical operation or operations that will happen to the input value and then generate the associated output value. So remember, a function has input and output. And in a few minutes, we'll talk about how the input is usually associated with x, and the output is generally associated with y, and that we can write our input-output in an ordered pair form like we've just seen. A function has to be dependable. So for each x, there is one and only one y. Another way to say that is for each input, there is one and only one output. The function rule will tell you what the operations are if you're talking about an algebraic type function. Or in the case of this drink machine, the rule is when you press a certain button, you get a certain output. Now here's where that input-output being dependable is important. You've got to have this dependability. For example, if a person walks up to this drink machine and selects button number 2 here, so their input's 2, the output that is expected, as you see here, is Diet Coke. Now that's not numerical because this is not a numerical machine. This is actually a function, but it serves a different kind of purpose. It actually delivers a soda based on the input that you put in. And if a person walks up behind you and presses that same button, they should also get a Diet Coke. That's what makes this a function. because for that input of the second button, each and every time, there's only one possible output. You can depend on it. Now, of course, there are cases where that might not be true if the machine has been loaded incorrectly. But if everything is working the way it should, if this drink machine is a true function for the same input, you would be guaranteed and be able to depend on that output. So we use a function notation that looks like this. Y is a function of x. And really, that is output is a function of input. What you get out depends on what you put in. Just like with the case of the drink machine. The drink you get depends on the button you press. That's what makes it a function. The output is a function or depends on what you put in. In the case of this function, its name is f. Very common letter used for the name of a function, obviously the letter f. You'll see others in this presentation, C, H, R. All of those are pretty common names for functions. Input is going to be your x value, typically. Sometimes you'll see the value t, often used as an input value, but we typically think of it as our x, and in this notation it certainly is the x. Output is y or f of x. This entire notation, f of x, means the output value for a certain value x. And the rule is not given here, but remember the rule is what tells you the operations that occur to the input value to produce that desired outcome value. Your rule has to be dependable. So you don't, in other words, you've heard changing rules in the middle of the game. Well, you don't do that in a function. The rule is the rule, and the rule is the same for everybody. So again, going back to that drink machine, you press button number 2, you always get Diet Coke. Now here's a pretty common looking function. C of x is 4x plus 6. This happens to be the same one we did a few minutes ago when we graphed y is equal to 4x plus 6. We've simply replaced the name y, or output, with the name c. So this is a function called c, and later on you're going to see that this is actually a cost function. Then that's why I chose the letter c to represent the name of the function. Our input is x. And we'll see in a few minutes that x is going to actually be the number of scarves in an application situation. Now the output here is the cost, or c of x. That is, what do we get out if we put in a certain value for x? And the rule is the 4x plus 6. It says, for every x that goes in here, you get a c of x, which is going to be a cost that you'll see in a few minutes. And the rule, or what happens on the inside here, is take that value x, multiply it by 4, and add 6. So we might do one like c of 3. That means x is 3 going in. Inside the function, we do 4 times 3 plus 6. That's 12 plus 6, or 18. So we would say our output, c of x, is 18. In 3, out 18. It can be written as an ordered pair, 3, 18. X, c of x, or xy. Remember that the function name here is just c, depends on a value x, and it would be the same as the y coordinate when we graph. So our c of x would be the value of y, or the y coordinate when we graph. So we would plot a 3 for x and an 18 for y if we were going to graph this. So, same function. C is a function of x. The value of C depends on what we pick for x. The name is C. Our input will be some value of x. Our output will be what we get when we put x into the rule for C. Our rule, 4x plus 6. So we could plot the points like we did a few minutes ago. If x is 0, we have a 6. If x is 1, we'd have a 10. If x is 2, 4 times 2 is 8, we'd get a 14. And so remember a few minutes ago we got that line that came through these 3 points. Again, this is a very rough drawing. You would want to use a calculator or a straight edge to actually draw it. And so I'll show you a cleaner graph in just a few minutes of this. All right, so back to our graph that we were doing earlier. And so in this case, instead of using the value y as the name of each of the functions, or for the output value, I've used c of x and r of x. And I'm just going to pick some numbers here at random. These will be different from the ones we used a few minutes ago, but I'll use the same ones. Do the calculations. And then write my ordered pairs. You should go back and check the arithmetic to make sure that you agree with these. And just as a reminder, the way that I calculate my output or y values, or in this case c of x value and r of x value, is to substitute this into the proper function. You put in a 0 here, you get 0 plus 6, so I get a 6, ordered pair 0, 6. And in this case, this would be actually x and c of x. And in the second case here, this would be x and r of x. Because remember, instead of using y, I've used c of x and r of x. And then I could plot these points and take a look at what these graphs look like. And you will see, again, that there are 2 lines, and they do intersect at a certain point. And so I've taken the time to draw these in, and you can see that there's actually a point of intersection here. And this point of intersection actually means something in the context of a problem that we'll be solving in a few minutes. Again, the main point to understand here, however, is that we're still dealing with x's and y's and plotting points. The main difference here is the notation that we're using. For our input value, we'll still call it x. For our output value, our y coordinates, we're now calling those c of x and r of x because they depend on the value that we pick for x. So I'm going to take these same equations that we've been looking at and do an application problem and use these graphs and equations to help us solve the problem. So we have a context here where Janine is knitting scarves to sell to make some extra money. The upfront supplies that are needed to get started will cost her $6. She estimates that the yarn for each scarf will be $4. That's where this cost, or C of X equation, comes from. X is the number of scarves. $4 per scarf. This is a variable or changing cost, plus a flat upfront fee of $6. That's what makes a per cost equation or cost function. Now it also goes on to say that she plans to sell the scarves for $5 each. Again, where X is the number of scarves, 5X would be her revenue. So this is what we call a cost equation, and this is what we call a revenue equation. And these are pretty common kinds of equations you do in business applications, and we do use C for cost and R for revenue. These are the functions that represent her cost and revenue. Again, cost being money that she has to pay out in order to get this business going. And the revenue is the money that she takes in as she starts to make and sell these scarves. Now we're asked to find certain values, graph them, and then interpret the meaning on the graph. So doing a little calculation on the side here, C of 0, C of 6, R of 0, R of 6, and let's change this. This should be R of 3 minus C of 3. So we'll need to find R of 3 and then C of 3 and then find the difference or subtract those two. So in order to do this function evaluation, you just take the input value, which is X, the number of scarves, put it into the appropriate function, either cost or revenue, do the function rule, which is either 4 times the number of scarves plus 6 or 5 times the number of scarves, and then get your appropriate output values by doing the actual arithmetic. So just verify these numbers here. Cost of 0, 0 for X, 4 times 0 is 0, added to 6 is 6. C of 6 would be 4 times 6, 24, plus 6, 30. R of 0, this time input value 0 goes into the R function. Instead of X, we put a 0. R of 0 is 0. R of 6 would be 5 times 6 or 30. R of 3, 5 times 3 is 15. C of 3, 4 times 3 is 12, plus 6 is 18. Calculation-wise, this is not a very complicated function. But let's interpret these and then talk about graphically what they mean. Graphically, you're just going to plot these ordered pairs, just like we did before. Just remember, input is always X, and output is going to be Y. So it's not very difficult to plot these points. Just find those points. 630, here's 5 over 630, somewhere up here. 0, 0 here. Revenue at 6 is also at 30. R at 3 would be over 3, up 15. C of 3 would be 3 to the right, up 18. And you would come up to that same graph that we had just a few minutes ago, where you have an intersection point at 630. Now let's find the interesting thing, the R of 3 minus C of 3. R of 3 is 15. C of 3 is 18. R of 3 minus C of 3 is 15 minus 18, or negative 3. What does that mean? If Janine makes and sells 3 scarves, she loses $3 because she has only brought in $15, but she's paid out a total of $18. So she is in the hole, $3. Now, we talked a few minutes ago about how important this break-even point is. This is the point that tells Janine that she's got to make and sell at least 6 scarves. Otherwise, she's going to be losing money like we saw in this example. Again, we'll come back to this kind of application. The most important thing here is that you understand the input value, how to get the output value by following the rule of the function, and how to plot these ordered pairs, X coordinate, comma, Y coordinate, or input, comma, output. Now, one of the biggest mysteries in math something we call math modeling, is finding the rule for the function if you know input and output values. And we'll actually spend over this next unit a great deal of time learning how to do this. But in some cases, it's not that complicated. So I'm just going to give you a couple of quick examples to show you sort of where we're headed. Let's say I'm thinking of a function rule called f, where x is our input value. And I don't know what the rule is, but I know these ordered pairs. That if a 1 goes in, a 3 comes out. If a 5 goes in, a 7 comes out. And if a 9 goes in, an 11 comes out. So by observing what's happening here, I can look at the relationship between the input and output, and I can come up with a rule here that I think you'll agree with, and that is that you take the input value and you add 2 every time. Now, test the rule to see if it's valid. For example, input 9. When I input 9, if I add 2, do I get the output that's correct? 11? Yes. Input value 5. If I input the value 5, I add 2 to it, do I get the output value 7? Yes. So here is our function rule. Not a complicated function. We will learn how to find these function rules. It's one of the most useful things of mathematics that there is, and that is to be able to take a set of input data and output data, look at the relationship between them, and come up with that rule of what happened to the data. And you'll actually see one that's fairly complicated here in just a few minutes.